Everyone, so let's now talk about height fields. So height fields are another way of calculating collisions. And like the name suggests, what a height field is, it's actually a field, so it is a volume. And it's a bit strange because it's a two-dimensional volume and it saves heights. So what this is usually used for, before we look into the use case for our effects work, when you type in height field, you will find that there are all kinds of nodes, so quite a lot. So this is actually not only used for collision calculation, but mostly what this is used for as well is terrains, so landscapes and stuff like that. I will not talk about this in this video because this is an effects course. But if you Google height fields and Houdini, then you will find a lot of this stuff, how to create landscapes. And it's a pretty powerful tool. So let's look at the images, for example. It's all landscapes. So really wide areas of basically ground in different variations. So we look at the mountain node, but this is not even remotely enough for this kind of stuff. Height fields come in as a very efficient way of creating super high detailed, huge areas. Again, we will not talk about this, but I definitely want to mention that so that you're aware that this is an interesting topic that you can use height fields for as well. The way we will use it though is collisions. And as an example, and I know it looks a bit stupid, but it's a good way of explaining the problem. We have a grain simulation here, and it basically looks like that. We have a source, and then we have grains, and they're simulated, of course, via PopGrains node. I didn't push the substeps too far. And we have the collision object coming in that looks like this. And when we look what happens when we run this, you probably expect this to happen because we have a combination of 3D geometry scattered on top of a flat surface. We will not have a proper collision for this, because the flat surface will not be covered by the default SDF that is generated inside. So we will get this kind of result. Speed-wise, we are roughly at 4 frames per second or something around those numbers, but the collision is wrong. Of course, we know what we can do. In the static object, we can switch from the default SDF representation to something that works for flat surfaces, and that is use surface collisions, which looks like this. The disadvantage of this approach is it will be very slow. So if I press start, I drop to the frames per minute visualization. So it's really, really slow. So what can we do to solve this? You guessed it, we will use height fields for this, because height fields are kind of something in between. There are a volume that is flat. So what does that mean? To understand this a bit better, we just have to create a height field, and then we will see. The first thing you need to do is you create a height field, empty height field node that creates a height field for us. And the first thing that is a bit weird, it creates this massive grid here, which is actually 1 kilometer by 1 kilometer in size. And we know why, because this is usually meant for creating landscapes. So let's lower this to something that makes a bit more sense for our case, maybe 3 by 3 meters. We'll probably change this. And what we now do is we project our geometry onto this height field. And again, what a height field basically is this is a two-dimensional volume. So it's made of voxels that you can't see, but when you middle click, you can actually see there is a voxel amount of 4 currently, and we will fix this in a second, but this is actually a volume. And this volume only knows 2 states basically, above and below, because it saves in its voxel, which is two-dimensional, just a height. This makes it very effective, and to use this, we have to project our geometry onto this volume. And for this, there is a height field project node. It has 2 inputs, the terrain, which is another word for the height field, and the geometry to project. And when we look through it, something happened. But when this is our object here, I just realized I have to make my height field a bit bigger, maybe 10 by 10 should work. Yeah, you can see something happens, but it looks really wonky. It's kind of deformed the height field. Now, as we've seen, currently the height field only has now 25 voxels, so we have to increase that to see the result. And we do this actually with a grid spacing, because the grid spacing basically means the size of 1 voxel. So let's lower this, and now you can see that the detail is coming in. And actually, let maybe set this to 0.005. And now you can see what a height field does. It's almost like it's wrapped from the top around the geometry. And there's actually, as you can see here, there's a problem. The lowest part of our bowl here is not the lowest part of our height field. And this is because the height field has a minimum height. This is called the initial height. So we can lower this to maybe -1. Now you can see the whole thing goes lower. What's happening here again is this is a volume that is two-dimensional and it only saves in each voxel the height. And this way it creates kind of a very simplified surface that only holds the information where it is in height. This allows you now to very efficiently represent this geometry as a basically ground if you want. And if we put this into our geometry collision, we can actually now use this for collisions. The only problem is we have to change the way this is interpreted, because in the static object, it will currently still turn this into a surface collision. So I'm not even sure if this will work. Yeah, it ignores it, it doesn't work. So what you have to do is you have to go back to solver default so that it actually calculates it as a volume, or you just set it to volume. Actually, let's do this. And then you have to change the mode from ray intersect so it does not create its own SDF, but to use a height field as an input. Here it is. It actually has a mode for that. So now it will actually use this height field as an actual height field. And by the way, when you use height fields, the uniform division doesn't play a role anymore because the resolution comes from the height field itself. So you can completely ignore the uniform division here. And the advantage of this is when we look from outside again, it's very fast, as you can see. We have all of a sudden more than 4 frames per second. We have 5 frames per second, so a little bit faster than before. But you can see when we look at it together that it actually gives us a very accurate calculation of the collision. And also it's doing the whole thing very quickly, very fast. So great. Well, so why don't we use height fields for everything? Well, because you've already seen the problem. The height field is only two-dimensional. So for each voxel, it can only hold one height information, which means it cannot save more than one height per voxel, and that means it only saves the highest part of our geometry. So if we look back at our original, you can see here we could have gone below our geometries, and this will be completely cut off by the height field. It can only go straight down, it cannot go inside of something. So stuff like holes or caves or something like that cannot be represented by a height field. Let me show you a graphic to explain this a bit better to you. So we already seen a way of representing an object or collision object in form of a volume, and that is an SDF. So a voxel that is inside of an object saves the distance, and then it's negative, and the distance outside of the object that is saved is positive. In this way, we always know if there's a collision or not. This is already a pretty simplified way of representing an object, but we can make it even simpler, and that is a height field. Because a height field only saves a height in a two-dimensional volume, and this would basically represent this line here. And everything above it is above, and everything below is considered a collision. So really simple to understand and to check against. Which is fine for something like a ground, or maybe even something more weird like a cup, for example. Let's say we want to add some fluids into this, then sure, we only care about the inside part. So a height field would look like this. And then we don't care about any holes or cave-like, inwards parts. Only the highest point will be saved, and this is totally fine here. But in cases like a cliff, for example, and imagine you would have a fluid simulation coming here from the side, then a height field simulation would not work because you cannot properly represent this shape by just saving a single height information. Because, for example, at this position here, you have basically the ground maybe, and then you have the cliff, and then you have the lower part of the tree and the top part of the tree. So multiple heights here theoretically that need to be represented, which the height field can't. So as we've seen, a height field is a really cool tool. It's kind of the third way of creating collision calculations. We've already knew SDF. We knew surface collisions, which are accurate but slow, and the height field is kind of the best of both worlds, but has one big disadvantage. It cannot represent cave-like, inwards parts of your geometry. And this is why I only show it to you now, because it's not suitable for every case that is out there. So for example, if we look at one of our very first pop examples here, where we have our two boxes here and some points that collide with this would not work well with a height field set up. So if we would do this with a height field, it would look like this. The height field would only save the highest point, so the collision will also happen here on the edges, and obviously this is not what we want. It would not be a proper representation of the geometry, and if we would merge the base geometry with the result, and maybe we only take out the pops, then you would get really weird results when using height fields here. So this is a good example where it wouldn't work. So we will use height fields later on in a couple of examples, for example, fluid simulations. So for now, I hope that made sense. So thanks very much and see you later. Cheers.